Hi everyone. Today we're going to work our way through sketching logarithmic functions. And so what you'll see on the screen right now is what would be the ugliest log graph that we could encounter based on the transformations we know. So when you take a look at question 1, if I asked you to describe the transformations from that original or base log graph to that big ugly one on the side, hopefully we're good with all the key components to that. All of our outside, inside, vertical, horizontal still applies. The biggest idea for us, though, is to take a look at that and recognize that since we are talking about a log function, inside refers to inside the log, outside refers to outside the log. And so you'll notice both key components, A and D, that are outside the log affect the graph vertically. Both key components that are inside the log, B and C, affect the graph horizontally. And so nothing is really different when you take a look at a log graph compared to an exponential, quadratic, any of the functions that we've dealt with transformations in the past. Okay, I want you to just scan all the way down there and make sure that we are good to interpret all those transformations because they're going to be needed for today. What I want to do is I want to take a look at a situation that can arise that's a little bit different dealing with log graphs. So, very quickly what I want you to do, take a look at the graph in A. Y equals log x from base 2. The instructions for the problem, sketch each function on the grid provided. So I've given you a quick set of axes. And then below, we're going to state the domain for each graph. So very quickly what I want you to do is I want you to put y equals log x from base 2 on that leftmost set of axes. I would argue to you, you are where you need to be if you could put down a very quick sketch of that in 10 to 15 seconds. So pause the video right now, give it a shot. Okay, we're back. And so hopefully we notice that we have a base 2. 2 is larger than 1, so therefore it's an increasing graph. And so I'm going to have an increasing log graph that looks something like this if we increase through 1 with our vertical asymptote at x equals 0. So as I said, between 10 and 15 seconds to be able to put down a transformation for that graph. What we're going to do is we're just going to jump into graph B, and then we'll kind of work our way back to A to finish off the problem. So on graph B, what I'd like you to do is I'd like you to take a look at that because you're going to notice that there is something different in the equation in B than you've ever encountered before. Do we notice the exponent on x? That nowhere previously did we interpret an exponent as a transformation. And so I'm hoping that this one isn't as much of a jam for us, but instead we recognize that we have properties of logs that allows you to bring that 2 out in front since it was the exponent on everything inside the log. And if we were to view it using the blue equation, then we now have the means to be able to sketch that. We recognize that we have a 2 that is multiplying on the outside of the function, and therefore I have a vertical stretch by a factor of 2. So what I'd like you to do is just put on a quick sketch of what 2 log x from base 2 would look like, and let's try to make it relative the first graph. So whatever shape your graph looks like on the left for log x from base 2, let's try to draw something that would look like a vertical stretch by a factor of 2 on the middle grid. Go ahead. Okay, we should be back with a little confirmation. Pause the video if you need some time. So if I was to do a vertical stretch by a factor of 2, then that's not going to affect my x-intercept. However, I'm going to stretch everything vertically by a factor of 2, so it's going to become a little steeper. This portion that was flat is going to become a little steeper. And maybe I get something like that in blue. I notice I still have my vertical asymptote at x equals 0, and we're good. Okay, What I'd like to do now is I'd like to jump back to graph A and just address the second part of the problem to us, which was stating the domain of the function. So if we hop back onto graph A, we'll notice that my x is on the inside of my function. And if I was to look at the equation, then that would dictate that my domain would state that x must be positive. But also I can take a look at my graph, and I notice that my red curve exists entirely to the right of the y-axis, and that is where all my x values are positive. When we take a look at graph B, let's deal with the same thing. I can look and see my graph and notice that my graph exists entirely to the right of the, and so therefore, when I state my domain, x must be greater than 0. However, maybe we can see that there's something a little bit different with my function. That if I were to go back and examine where my x is on the inside of my log. But I also notice what's attached to it, the squared. And I know that regardless of what I sub in, as long as I do not sub in 0, my outcome would always be positive. As soon as I square it, it's always going to turn negatives to positives or keep positives as positives. And so therefore, when I wrote down my domain, I made a mistake. That I am now able to sub negatives in for that x and still calculate the value of my log. The only value I cannot sub in is 0. That tells me then that x cannot equal 0, but it would be anything else. Now I have a bit of an issue, that I recognize my domain is that case. However, my graph doesn't match that. Maybe we can see how we can make our adjustment. Notice that if I was to sub in a -1 for x, then when I square it, it becomes 1. And 2 to what exponent gives me 1? That is 0. That would tell me that I would also have this point over here, -1, 0, that would be a point on that graph. And maybe we can see that we would have the mirror image of that blue curve that would also exist on the left side of the y-axis. So this is a very weird scenario for us. And when we take a look at it, we can kind of see it as almost like a reflection. Here's the problem though, that it's not really a reflection, because when we reflect a graph, it's no longer in its old position. And so what you notice then is we have the new graph that's been reflected on the left, but we still maintain the old graph that exists on the right. And the way we describe that then is as a reflected branch in the y-axis. Notice that because of that exponent 2, we ended up creating a whole other branch of this function. And so we would describe it as a reflected branch. How do we get it? We reflect it in the y-axis. Now, this begs a very important question. That if I were to give you this function, y equals 2 log x from base 2, then doesn't properties of log say that I could always just put that 2 back inside, and so wouldn't that graph also have a reflected branch? And the answer to that question is no. The way we interpret domain is based on the original function. It's based on the form given. And so you'll notice in the original equation, my exponent of 2 allows me to sub negatives in. The squared is going to turn them to positives, and therefore I can calculate. In the second option, I cannot sub in negatives for my x because there is no squared. I may choose to put that squared there, but the squared is not there in the original function, and therefore negatives cannot be a part of my domain. Okay, I'm hoping that we're good with this new type of transformation for us, this reflected branch. Let's take a look at C. We should be able to pick up the pace pretty quickly on graph C. We recognize that we can bring that exponent 3 out in front to figure out the shape of the graph. We're going to have a vertical stretch by a factor of 3. And so my x-intercept isn't going to change, but now my graph is going to become even steeper relative to the other two. I'm going to have my vertical asymptote at x equals 0, and I'm hoping that we recognize that there would not be a reflected branch in this case. Let's make sure that we don't put the idea in our head that, oh, okay, so as soon as I have an exponent, I always have a reflected branch. No, that's not the case. Because you'll notice that when I have an exponent 3 on my graph, yes, that means a vertical stretch by a factor of 3. However, that 3 is still going to make any value you sub in for x that's negative stay negative, and therefore be undefined. So for us to state the domain for that last graph, your domain is still that x must be positive. Okay, we're going to jump in and we're going to deal with 2 sketching problems so we can see the process we would go through in order to sketch a function. So I want you to take a look at the instructions in question 3. We're going to sketch the graph of that function. And very similar to our exponential graphs, we're going to have 3 properties that we need to label: the x-intercept, the transformed intercept, and the asymptote. So this first step I'm going to go through, but it would never be required for us. It's basically just that log graphs are still relatively new. We see that we have a base 2 on that graph. And so we know that that is an increasing curve. And if it's an increasing curve, then I have my base log graph that would rise through 1 and level off. I would then have my vertical asymptote at x equals 0. That is the graph that we're going to be performing those transformations to. So I'm going to get rid of all of that gold, but that is the graph that we are going to be able to work our way through. So the first thing we need to do, since we recognize it's an increasing graph, is maybe we go through and we find all those properties. So the first thing I can do is I can find my x-intercept, because I know to do that means my y value equals 0. So I can replace my y with 0. And now what I've done is I've created a log equation. My variable is inside that log. I've got to get it out. So the first thing I can do is I can get rid of that +1 on the end. I'm going to isolate my log term. And so if I get rid of a -1 or +1, then I need to subtract 1. Next thing I need to do is to divide out the -1 coefficient on the log. So now I have isolated my log. Anytime I have a log equal to a number, I'm going to change that to exponential. So 2 to the exponent 1 is going to give me x minus 3. And then I can calculate and get my x value of 5. So there is my new x-intercept on my graph. The next thing that I can look at is examining my transformed intercept. However, to find out my transformed intercept, I need to be able to interpret all the transformations in my graph. So I am going to be taking the point 1, 0, which is where every log graph has an x-intercept, and I'm now going to transform it. So first thing I'll notice, my negative out in front means reflect across the x-axis. Well, reflecting a point on the x-axis across the x-axis means it's invariant. There is no change. The only other things to do then is to interpret the -3 and the +1. And so we are going to shift my curve to the right 3 units and up 1. My transformed intercept then has the location 4, 1. So I have 2 points on my graph now. Now what I need is I need the location of my vertical asymptote. And so I know that every log graph has a vertical asymptote at x equals 0. I need to then do all those transformations to it. So reflecting a vertical line is going to cause no change. Shifting to the right 3 will cause a change. However, not a +1. And so the only transformation that's going to affect that is going to be that shift to the right 3. And so when I shift my asymptote, I finish at x equals 3. Now, for some of us, we're also going to take a look at that and notice that x equals 3 is the value that gives me a 0 on the inside of my log, therefore making that log undefined. Some of us will arrive at our asymptote using that theory. So I now have my 3 properties. I'm going to go ahead and I'm going to label them all on. I like putting my asymptote on first because that's going to act like the wall where I know my log graph must exist entirely on one side of it. Now I have 2 other points. So what I'm going to do is I'm going to locate 5 would be about here then. And I can now plot on my transformed intercept that's a little bit less than that and a little bit up. I'm going to use the connection of those 2 points and the nature of the curve to give me a little confirmation as to whether my graph's correct. So the only way that I can connect those points and approach the asymptote was if I was to go through and then say, well, these 2 points would have to cross and this would have to approach my asymptote. So my curve would have to look something like this. Hopefully we can see that should confirm it for us. However, I want to jump back to what our base curve looked like so that we can see that we have a pretty good looking sketch. If you recall, this was our base curve. When I examine everything in my original graph, my original equation, I notice that the only thing that's going to affect the direction of that curve is going to be this reflection. Shifting a curve does not change the shape. Reflecting a graph can change the direction. And so if I was to take that gold original curve and reflect it in the x-axis, I get a little bit of confirmation that now if I was to shift that, my curve is going in the right direction. So there you go. The only things that you do not need on that graph are anything that is original. So I'm going to get rid of that original curve. If you can show your asymptote, your transformed intercept, your new x-intercept, the actual x-intercept of the graph, and then connect them all with a smooth curve, you've got a good sketch. Okay, what we're going to jump into now is going to be probably the ugliest sort of sketch you could be asked to do. So I want you to take a look then at how ugly that graph is that was given. There is so much stuff in there. We're going to take our time and we're going to work our way through it. So the first thing we may do is to go through and find all the properties of that graph that we're going to need to label. So the first thing we're going to do, we're going to find our x-intercept. So for me to find my x-intercept means that my y value is equal to 0. So I'm going to make the substitution of y equaling 0. And now I notice that I've built a log equation. It's time to go through and solve. So the first thing I need to do is to isolate that log equation. Now, when we take a peek at that, I would hope that we could isolate the log term by getting rid of the other term and dividing out that coefficient at the same time. And so to get rid of a plus 12 means I subtract 12, and then to get rid of a times by 3, I divide by 3. Please feel free to jump straight to that as your first line. Now, we take a peek at that function, and we should be good. The next step for us then is, since we have a single log equal to a number, is to change that into exponential. So 1/3 to the exponent -4 gives me that expression. Now, there are a couple things that I would recommend if I were you. The first one is, let's try to evaluate the power that we have on the left first, if we can. You'll notice, and I'm just going to hop in here a little bit and do a little bit of writing, that 1/3 to the exponent -4, for me to change the sign of that exponent means I could flip the base. And so my left side is really equal to 3 to the exponent 4, or 81. So my recommendation to you then would be, let's go ahead and let's evaluate whatever we can on the left. So I can change that then to 81 on the left is equal to, well, now for me to get my x all by itself, I have to get rid of the squared. To get rid of a squared, you take the square root, and every time I take the square root, I get 2 possible solutions. Now that I have that, I can divide out my 4. You could have expanded in the 4 if you wished. Now to get my x all by itself, I need to get rid of my +1, which means I'm going to subtract 1. So I'm going to have -1 plus or minus 9/4. And so I can now calculate both my x-intercepts. I'm going to have -1 plus 9/4, which is a 5/4, or I'm going to have -1 minus 9/4, which is a -13/4. So we have 2 x-intercepts. Now, that shouldn't surprise us. And as we move into finding the transformed intercept, that 2 up top should be screaming at us. We should see then why we have 2 x-intercepts. What does an exponent 2 mean for our graph? That tells us that we have a reflected branch. So we shouldn't be surprised then that our curve crosses the x-axis in 2 different spots. Okay, for us to get the transformed intercept, we're going to have to deal with all the transformations. And so the first thing we can then deal with is, let's bring that squared out in front so that we can interpret as a stretch. So for me to deal with my transformed intercept, I'm going to have my original intercept, and now I need to transform it. Well, what are all my transformations? With that 2 out in front, I'm actually dealing with this graph to be able to determine its shape. And so I can see that I'm going to have a vertical stretch by a factor of 6. Well, that's going to have no change on a point that's on the x-axis. I'm going to have a horizontal stretch by a factor of 1/4. That is going to change. That transformed intercept is then going to get transformed to 1/4 0. And now I can go through and I can shift my points. Now I shift my graph 1 to the left, which means I'm at -3/4 0, and then shift it up 12. So I arrive at -3/4 12. There is me working my way through those 4 transformations to arrive at my graph. Okay, the big part in our head now should be, hey, what about the reflected branch? Yes, the reflected branch is a transformation, and we have to remember when we do reflections. So as long as we make sure that we do reflections before our shifts, then we're good. So I'm going to go through that exact same process, this time in gold, but incorporate my reflected branch. So I'm going to start off at 1, 0. And now I vertically stretch it by a factor of 6, no change. Horizontally stretch it by a factor of 1/4. So that gets transformed to 1/4, 0. Now I'm going to deal with the reflected branch. And so I'm going to reflect that across the y-axis so that I'm now lying at -1/4, 0. The only things left to do, shift it to the left 1, which puts me at -5/4, 0, and shift it up 12. And I now have the location of both transformed intercepts. The only last thing to deal with is to deal with our vertical asymptote, and our vertical asymptote is probably the easiest thing to come by. A vertical stretch by a factor of 6, no change. A horizontal stretch by a factor of 1/4, no change. Shifting it up 12, no change. The only thing that's going to affect it is the shift to the left 1. Now that we have all those properties, what I'd like you to do is just pause the video, and can you construct your graph that satisfies all those properties? So go ahead and pause it, give it a shot now. Okay, we are back. And so the first thing I'm going to put on is my my vertical asymptote at x equals -1. I then have two x-intercepts. One that's at 5/4, so that's a 1 1/4. So I might be somewhere out here. And I'm also going to have another one at -13/4, so like -3 1/4, so -3 and a bit. Maybe made that one a little wide. I also have two transformed intercepts. So I'm going to have one that's going to be at -3/4, so like just a little bit to the right of -1 and up 12, maybe here. And a -5/4. Well, I think I can see how I'm going to put those all those points and approach my asymptote together. The way I can do it is to come up and connect and extend, to come up, connect, and extend. I got a little wobbly on that one, and there we go. So, as I said at the very beginning, the function you see in 4 would be the ugliest function that we could ask you guys to sketch. So, I know that there was a lot of information in this lesson. What I want you to do now is get some practice working through on those sketches. Okay, good luck.